Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to welcome Byron Cook. Most of you know Byron from MSR Cambridge, so he's going to talk about some new ideas in termination proving for programs.
Thanks. Okay. So if we think of all the tools for doing automatic software verification, we could sort of try and throw them into two buckets, right? So you could think of the one bucket being those tools that take a program and a property and try to verify that property or die trying, right? To slam it, don't come back until you've verified this property, right? Keep working. And the other set of tools like S3 or Sting or Octanal, TVLA, are tools that are designed more to try and prove as many properties as possible from a given set, right? So here we're given one property, whereas these tools typically don't care what property you're out to prove. They just prove something, and hopefully that is what you were out to prove. And if not, then maybe you do something and recall it in a different configuration. Maybe that will now prove what you were after. So, and of course, there's a spectrum. So there are many tools that live sort of halfway in between, and these tools call these tools, and so on and so forth. But think of those two extremes on the spectrum. So in some futuristic version of Visual Studio, for example, you might imagine putting your pointer here, and then asking the tool, what do you know with these tools that prove as many things as possible as quickly as possible? So it might say, for example, that at this location, we know that x is greater than a, y is greater than b, and the program counter is equal to location 260. Right? Do you see why that's true? We've just gone into the while, so it must be true, right? And then you could move your cursor around to other locations and ask for here, for example, at line 262, what do we know? So now we've lost the correlation about x because we don't know how many times we've decremented x, but we still know that y is greater than b. Right? And over here, at this point, we could ask the same thing. And here it would say that x is greater than a still, but now because we've decremented y once, now y is greater than or equal to b as opposed to greater than b. Right? And these invariance analyses typically will do something smart at the join points where you have an invariant here and an invariant here. So here our analysis might say something like either y is greater than b, or x is greater than a, and y is greater than or equal to b, right? Or they might so the invariant here is the disjunction of these two conjunctions, or they might merge them together and build one conjunction that represents the over approximation. Okay, so that's these invariance analyses, and they can be built up over various domains. This, for example, is the octagon domain where we have two variables per inequality, but you could choose different kinds of domains. Like you could choose polyhedra separation domain, whatever you want, right? And there's a plethora of these tools now available, plethora of domains, and people have been working on this for quite a while. And the constraint to these tools is that they all are restricted to safety properties, right? So the invariants that are proved or are inferred are all safety properties of the programs, right? And that's been true both of the software model checkers, or these tools that go off and try and prove a single property or die trying, and these tools for quite a while. And in recent work that many of you know about, there's a tool called Terminator, and there's another tool called Polyrank, and there's several other tools now that are available that extend these tools for doing safety properties to infinite state, for doing termination of infinite state systems, but we have nothing analogous for analysis. Right? So the question that this talk is addressing is what would tools in the analysis world look like for termination? Right? Could we come up with a tool that proves as many things as quickly as possible that has something to do with termination or liveness properties? Okay. So I have a proposal for you, Shvindu. I propose that we call, so we're used to something called an invariance assertion. Right? An invariance assertion is something that holds at a particular line. So it's like a formula that's guaranteed to hold during the program's execution at that line. Right? So we'll call a variance assertion a formula that's actually a transition predicate or a binary relation on states that holds between any two states, one that's reachable and one that's reachable from the first state. Okay, so it'll actually be a binary assertion holding between two states at location n. Okay, and we'll call and as a sort of special case, we'll have something called an isolated variance assertion, which is the same as before, but the execution from the first to the second state doesn't leave the enclosing loop. So if you have a location, if you have some line at location in, the execution from the first to the second state doesn't actually exit the loop that it's enclosed in. And then we'll talk about variance analyses, which produce as many as sort of the strongest possible variance assertions given some abstract domain. And so that's the subject of this talk. So what I'm going to do is I'm going to show you how to take any invariance analysis, like TVLA or some numerical domain or shape analysis based on separation logic, and construct a variance analysis. Okay, and then from that, I'm going to show you how to get a quick and dirty termination prover out of it. So in some sense, for any invariance analysis, we get a free termination prover. Okay? And so now we have a plethora of them, and we can call them and see. We can prove some programs terminating with some of the provers, and other programs terminating with the other provers. But the neat thing is that they're free. Right, and free's a very good price, and then I'll compare it to Terminator, which is the tool I've been working on for the past year or so. Okay, so first of all, what do these variance assertions look like? So here's an example of what we might expect a variance assertion to look like at the same line. So this is saying that, as before, x is greater than a. Y is greater than b, but the old value of x is greater than the current value of x. So the old x is the x in the first state, and x is the x in the current state, or in the second state. Okay, and so the disjunction of these three assertions then over-approximates. The idea is that these three are supposed to over-approximate all possible pairs of reachable states where the first state is reachable at this location and the second one is reachable at that location from the first state. Okay, and so what these do is they chart progress or change. So here we can see that. So if you look at any two pairs of reachable states, either x has gone down, or y has gone down, or they've both gone down. Yes. So the idea is we have any two pairs of states. So let your program run any amount of time. Take any two pairs of states, any state that's reachable at some time, and it should be at location n, and then any other state reachable from that state, this relation holds. The idea is that this relation should hold between those two states, and old of x means x at this state, whereas that's old. So of x, and this is x.
Logic notation
tick
would be the unprimed.
That's right.
The x would be x prime.
And the reason I'm not using primed is because sometimes people, because of model checking notation, they sometimes think that I actually mean the next one. But it's not the next one. It's any one afterwards. So I use a slightly clumsier notation so that we have this discussion ahead of time rather than sort of 20 slides into the talk. I don't care. Yeah, you don't know. It's just pick any two states. First one's reachable, second one's reachable from the first one. This relationship, one of these three conjunctions will hold between them. Yes?
I was going to say that first about the notation, that it seemed like a fine notation, and we used it in spec sharp, but now you said that it was clumsy, so maybe I won't point that out. But what you have there is these relations are it's not reflexive the way that you've written it. So in other words, you do one loop iteration and then any number of loop iterations. Apparently,
you do any number of loop iterations and then any number after that. But one or more after that.
One or more.
One or more after that.
Yep.
All right. So, and then you can think of this as a relation where it's a function from a state to something of type bool. So, sorry, this should be old of x and old of y, old of a, old of b to x, y, a, and b. Right. So that's the idea. Okay. So this is an algorithm that takes any invariance analysis and produces these variance assertions. Okay, we'll basically walk through the algorithm. That's what I'll do. So it takes a program and a set of locations, and so we're going to produce variance assertions at the locations in L, and this is some initial state of the program, but expressed in the abstract domain. So maybe it's true, or maybe it's program counter equal to 0, or something like that. Okay, so the first thing we do is and by the way, this variable is going to hold all the disjuncts. Right? So VAs is going to be a set of formulae, and we're going to chuck them in. And the idea is that after the analysis is done, the disjunction of all of these will over approximate this relation for all locations in L. All right, so the first thing we do is we run the invariance analysis, given the program and given the initial state. And so this just computes the invariance assertions, the standard thing. So here, for example, we have one of the elements of IAs. It's x greater than a, y greater than b, and program counter equal to 260. So, and you might, in this case, we just have one for location 260. And now what we're going to do is we're going to iterate over each location that we're interested in and essentially rerun the invariance analysis in a special way. So I'll show you what that is. Yes?
What is I#?
I# is the representation of the initial state of the program, but expressed in the abstract domain. So for example, true. Or that would mean the program could start anywhere. Or program counter equal to 260 would mean that we know nothing about the state, but we know that its program counter starts at 260. Precondition the program, but in the abstract domain. Right? Okay, so the first thing we do. So what we're going to do is we're doing this for each location. Ignore this for now. I'll talk about this in a minute. For each conjunct of the invariant at location L, where L is the location we're interested in. So as we look at Q, and if its program counter is equal to the one we're interested in, then we rerun the invariance analysis using Q, but after a couple of operations. So the first thing we do is something we call seeding, which essentially takes Q and encodes a relation in the abstract domain. Okay, so we introduce new variables, old of x, old of y, old of b, old of a, old of pc, and just set them to be equal to pc, a, x, y, b, and then keep the old q. All right, so the idea is we have now a relation from old of x, old of a, old of b, etc., to x, a, b, etc., such that on the second state, Q still holds. And so it's a restriction on the identity relation, essentially. Okay? But it's encoded in the abstract domain. So the invariance analysis, for example, doesn't know what the intended meaning we have for old of x and old of y. Right? It's just some other symbolic constant, some other variable, ghost variable or something. Okay, and then what we do is we take one symbolic step from the state. And the reason is we want to take one or more steps from the first state. So we just symbolically execute from the state one step. And so here we've done nothing. We've just incremented the program counter. And then we rerun the invariance analysis. Okay, so that gives us the disjunction of the conjunctions. Right?
So you're basically using something that doesn't compute binary relations
to trick it into
binary relations, and you're doing so by essentially introducing the self loop edge, which says that the new value of y is equal to the old value of y.
That's right.
And then you're running the abstract interpreter, which is only going to update essentially it doesn't know about old.
That's right.
Olds are like Skolem constants.
That's right.
They're uninterpreted, and okay.
Yeah, that's right. And then we throw them in the big bucket of variance assertions and move on. Yes?
I mean, all you're doing is you're saving away, introducing new variables that you can save just before the loop, and then the analysis does already keep track of binary and ternary and whatever operations that is.
Right.
And now you just have more variables.
Right.
And now what you need to look at to get the one or more iterations is that you need the 3 list boxes that you have there. You need to get those values from the points where you have the back edges.
That's right.
And then, other than that, it's just exactly an invariance computation. I mean, an abstract interpretation.
Precisely. Yeah, that's right.
You're just saving the initial values, and that's all.
That's what's for this given seed. That's what happens. Yeah. So the idea is that, and I'll talk about this a little bit in the later slides, is that for each abstract domain, you have to invent a seed operation. And for the numerical domains, it's fairly obvious what to do. For the shape analysis domains, for example, it's a little trickier. But you come up with the seed and plug it in, and I'll talk about this isolate business in a moment. But that's not really too much. And now you've souped up your invariance analysis, and now it's a variance analysis.
We do that part in Google as well.
Do you get the disjunctive? The disjunctive part is actually turns out to be really critical for us.
We don't use, what we do is we take we just widen those in back in, and we never output it as a variance analysis.
Okay.
But we do keep the initial values, and so we are computing those relations.
Right. Okay. Yeah, and so you see this in the literature quite a bit, where people under various names will introduce new ghost variables, or they'll freeze the state or various things, and then do some analysis, and that sort of gives them some relation. Well, and I'll talk about this more in a moment. The important point for us is that we need some level of disjunction, because this is going to give us power to prove termination, for example. Yep.
So you use this old X and old Y for termination, but a question to Houston, so what do you use this for? So you keep track of old X and old Y, but what benefit?
Just for, to produce loop invariants. So our loop invariants are, but they relate the current state to the initial state.
But do you take the fixed point again? So do you compute all possible next states, or do you take one path through the loop?
It will be the fixed point. So in fact, the disjunction here, I'm guessing that you actually keep the 3 disjuncts, and when you iterate, you might get more disjuncts, and you hope that eventually you'll get to fixed set of them. What we do is
no. We get this set of disjuncts, and that's it. We throw them in. And then we might get another set from another queue, but from this one.
So what we do is we just widen those together.
Oh, okay.
But the
okay. Well, no, actually, I don't understand. Well, we'll talk about it more. I suspect your invariance analysis doesn't produce disjuncts, though, right? Because these actually come from the invariance analysis.
If you want to pick up the disjuncts, you'd have to look at each place in the program code where there's the back edge,
right?
And
right.
then
push them around.
One, right.
Okay, great. Okay, now let me talk about this isolation business. So this is so that we can get these isolated variance assertions. So the idea is we want, during all of the states between here and here, we don't want the execution to leave the loop that the location in is contained in. So we actually modify the program that we pass to the second call to the invariance analysis. So we're trying to basically imagine that the location that we're examining is right here. So we want basically the execution not to leave this loop, right? Now we know that the analysis, the initial state on the second call to the analysis will be at this location. So all we have to do is limit executions leaving. So at all of the locations where the execution might leave, we put an assume false. Right? And this is sound to do because our first call to the invariance analysis gave us all possible reachable states, an over approximation. Right? So we're not missing cases where we enter and leave, because we we will, during the analysis when we're using the isolated invariance assertions, we'll have to keep track of the fact that there's an ordering on the locations and what's reachable from what. So we have to keep the control flow graph in mind if we use this. Okay, and so this is helpful if you're trying to prove termination of loops like this one, for example, where if we want to prove that you essentially can't reach this location infinitely often, in isolation that's true, right? Because you set k to be something, and you know that the loop will eventually leave because k keeps going down. But if you try and prove that this location isn't reachable infinitely often, it will fail because it's possible that you could come in and out of the loop many times. So what we're doing is we're saying you don't want to reach this. You want to say that the only way to visit this location infinitely often is actually to leave the loop infinitely often, and that's something we can prove with an isolated variance assertion. So it gives us a little bit more accuracy.
But isn't it true that for that program it is the case that it is not visited infinitely often?
It depends on what the outer context is, right? So whereas if we use an isolated variance assertion, it doesn't really depend on the outer context. Okay, so these are the ingredients we need from the invariance analysis. We need a single step abstract transfer function. We need the fixed point, the over approximation of the fixed point, and we need a way to construct initial precondition on the program. Okay. So if we can get that from our analysis, then we're ready to go. And I'll talk about this a little bit more later. We hope and pray that this invariance analysis does some level of disjunction, because the prover is, for at least for termination, it's fairly useless without it. And then seed is invented. So this is something you have to come up per abstract domain. Okay. So, and we know now after executing this procedure that we have, if the analysis returns a finite number of abstract formulae, we know that that this inclusion holds. That we have some finite number of relations whose union over approximates essentially the transitive closure of the program's transition relation. Where here, this is something called the in Terminator we call this the binary reachability relation. It's essentially the set of pairs of states where the first state is reachable. So that is, we can get from some initial state to S1 in any number of steps, and from S1 to S2 in one or more steps. And the program counters of S1 and S2 are equal to the location that we're interested in. So take that relation, this set of pairs of states, or the binary reachability relation. We know by construction that that T over approximates that, right? The union of all those relations over approximates it. Okay. Let me skip this. All right. So that is, we have our set of pairs, set of pairs here. All the elements S1 and S2, where the first one's reachable and the second one's reachable from the first one. You can think of that set. Typically, it might be infinite, but we know we have a finite number of relations whose union over approximates that. Right, and so that's what we're getting. Another way to think of this is. We take the step relation from the program, take its transitive closure, limit ourselves to pairs of reachable states, and limit ourselves to states whose locations are at L. So pairs of locations, pairs of states at location L. And we know that this is over approximated by the union T1 to Tn. Okay, so now what can we do with these variance assertions? So what I'm interested in is termination, but actually you could imagine using this to prove liveness properties also. So, but I'll stick to termination. So it turns out that we're for lack of a better name, we have a condition on each variance assertion that if we can prove, then we've proved termination. So basically, we run the variance assertion analysis, compute all these formulae, walk over the formula. For each one, if we can prove some condition, then we know the program terminates. And that's what we're going to do. So there's a in the literature there's from a couple of places. For example, Podolsky and Rybolchenko. There's a result that if you can take essentially the binary reachability relation and find a finite union that over approximates it, and that each relation in the union is well founded, then you've proved termination. Right, and in this context, we're saying that we've proved that the location L, the one we're interested in, isn't visited infinitely often, which is a slight adaptation. Right, and so this is a little bit different than the standard way of proving termination, where you find a single relation and then prove some inclusion. In that case, you don't have to take the transitive closure. Right, in this new result, you can find a union of well-founded relations. So the union is not necessarily guaranteed to be well-founded, but each element has to be finite. And then you take the transitive closure of your transition relation and prove this inclusion, and now you've proved termination. And this is the rule that Terminator also uses. So that is, if we run our variance analysis and we get some union or some over-approximation, if we can prove that each of these elements is well-founded, then we've proved termination. Okay, so do we all know what well-foundedness is, by the way? Does anyone not know? Don't be shy.
Yeah? Condition and not necessary condition, right? So each of those individually well-founded.
If you can prove this, you know the program terminates. But actually, no, it's the other way around too. It's the other way around too. You can find just a single T1. Right, that's well-founded and over-approximates transitive closure of your program. I mean, for example, you could just take T to be R, right? R plus. Okay. Okay, so in relation to the variance assertions, so here is the over-approximation at this program location, and if we can prove that each of these are well-founded, then we've proved that we can't visit this location infinitely often. Okay, and this turns out to be very easy, actually. So in the analysis, we walk over each relation in the variance assertions and call some procedure, and if that procedure fails to prove that the formula is well-founded, then we go into some array and set its program counter to be false. We initialize the array to true, and if no elements in the array are set to false, then now we've proved termination. Okay. So, and what we've proved is that in this case, line 260 is visited infinitely often only in the case that we leave the loop that it's contained in. Right? That is the loop from 259 to 267. So from here to here. Okay. And again, this well-foundedness check has to be invented. Right? So to get our free termination prover, we have to invent a seed and invent a well-foundedness check. Okay. So how does this compare to Terminator? Terminator implements basically the opposite approach. It goes the other way around. So in effect, our new approach is computing this. It already knows it computes an over-approximation, and it knows the over-approximation holds, but then is trying to prove that each element here is well-founded. Whereas Terminator is adding elements T1 to T in, and then checking the inclusion over and over again. Right? So now we're computing the inclusion and checking the argument, whereas in Terminator we're constructing the argument and checking the inclusion. So in this new work, we could imagine computing our over-approximation and then removing the elements that are not well-founded. Right? And then from Terminator's algorithm, we could then begin doing refinement. So we could find. So what Terminator does is it tries to check this inclusion, and if the inclusion doesn't hold, then we get some counterexample. So that is two states, one reachable and the second one reachable from the first one, and then we examine those states and then add some new well-founded relation based on some analysis. So we look at that counterexample, generalize, and add some new relation. Right? And this is how Terminator works. So we can, and this works by looking at that counterexample, doing rank function synthesis, finding some rank function that proves that particular path is not a counterexample to termination, and then building the relation of pairs of states that are ordered by the ranking function. And so that's the new relation. And we just iteratively try and build up this over approximation. Okay, and we might do it again, and we might cover it now, right? So we might have maybe found two counterexamples. They were both false counterexamples. We enlarged the termination argument and then covered it. Or it might be that these two pairs of states really did represent a counterexample. Right? And so in that case, we'll pass the counterexample back to the user. So that's how Terminator works. But today, Terminator starts from the empty set. It does refinement from there. But you can imagine combining the two techniques where you do some analysis. Hopefully you've proved termination. And if not, then you remove all the non-well-founded variance assertions and then begin iteratively trying to find an inclusion again. Okay. So I've promised you that we can make it a termination prover for free. Right? Or, well, not for free, but for very cheap. Yeah, we have to come up with a seed and a well-foundedness check. And we get termination provers. So we could maybe choose from the octagon domain or polyhedra domain, some shape analysis domain. Maybe we could take a signs domain. So we can take analyses that implement any of these domains, and now we get a free termination prover. And so that's what we'll do now. And you could think of the continuum of abstract domains from very expensive ones to quite cheap ones. Right? So we can choose any element on that line. And also, there's another line which is the fully conjunctive to disjunctive completion. So an analysis may choose some approximation of disjunctive completion along here. And we now can choose any point on that in this space and make it and get our free termination prover out of it. So we did 3 points on the space. So we took something called Sting, which is from Stanford and uses polyhedra, and we modified it using some recent work we found in the literature about how to take an analysis and make it more disjunctive. And we did the same for a tool called Octanel, which uses the octagon domain. And then we used a tool called Sonar, which implements shape analysis using formulae from separation logic. Yes?
You mentioned about going from a string to modified string.
I won't. There's a couple of recent papers that talk about how to modify the control flow graph of your program to approximate disjunctive completion, and we implemented one of those. I can't. They're both quite similar. So we basically take the program and we do a little bit of messing around with the control flow graph to add extra locations, and then you can look at the invariance at the different locations and take a disjunction of them. So it's some finite approximation of disjunctive completion. Okay. So, but we need to implement a seed and well-foundedness check, right? So here is the seed and well-foundedness check for arithmetic domains. So seed just takes the formula and conjoins it with a new set of equalities between V and old of V, where old of V is some bijection. Okay? So, and this is over the program variables. And the well-foundedness check takes the formula and calls one of the well-foundedness checkers that are available on the internet. So linsys or polysys or rank finder, for example. And we have to say what the pre-variables and post-variables are to the formula. So we say, it's the program variables are that represent the second state, and the valuation of the old variables represent the first state. And then we just call rank finder, for example. So here you can imagine taking some abstract state, x is less than y, program counter is equal to 10, and seeding it, and that gives us x is less than y, program counter is equal to 10 as before, but we introduce some new variables. Right? So this is what we did in a previous slide. And then you could imagine symbolically executing from this state across these three commands. So that would give us, in this case, the x gets x plus 1 should mean that x is 1 greater than the old value of x. The assume x is less than y gives us that x is still less than y. And the go to 10 means that the program counter is back at 10. And then we can call rank finder in the following way. We just take this relation and encode it in its input. So we say, here's the constraint. X is less than y. PC is equal to 10. X is bigger than it was before. And then we have to say what the pre-variables and post-variables are. So that's the input. And then I call this tool rank finder. And it says, indeed, this is well-founded. And it finds a ranking function. And this is the ranking function. So these are the coefficients on the three variables. So the ranking function is x times minus 1 plus y. Right? And in this work, actually, we just throw away the ranking function. And it doesn't matter. So we just just the existence is all we need to know. Right? So you can imagine even if the state was nonlinear, for example, that you could just prove it by hand, right? Or prove it in some theorem prover. And so long as you know that there exists a ranking function, or that is that it's well-founded, then we're done. So here are the experimental results with the four tools, actually. So I set the octagon-based tool and the sting-based tool against polyrank, which is from Stanford, and Terminator. And so I have three sets of examples. These are on examples from the octagon library distribution. So in this, these two are sorting algorithms. I can't remember which one is which. I think this is bubble sort. Oh, I'm sorry, these two. One of them is bubble sort, and one of them is insertion sort. And the check mark means that we found a proof. The dagger means that we found a false counterexample, and the dash means that we have no result, typically because of a timeout. And as you might be able to see, the octagon smoked the competition, right? So it's the only one that was able to prove them all terminating, for example, and was quite a bit faster than Terminator. Okay, and it's a little bit surprising that the sting-based tool wasn't so good. But and by the way, I should say that we actually implemented this one, whereas this is actually Dino Di Stefano stepping through the algorithm. So we just summed up all the parts of the algorithm. Okay, it's not quite fair to compare these because, for example, Terminator is trying to produce counterexamples, whereas these tools don't. And polyrank. Polyrank is quite bad when you hand it programs with control flow graph, right? If you just encode a transition system in sort of a very specialized way, then you can get the proof to go through typically. But you can't just hand it a program, right? And encode the program, just control flow graph with continues and breaks and so on and loops. Okay, so these are examples from polyrank. Okay, so we would expect that polyrank does quite well here, and it does. So here's the polyrank row. Only one of them turned out to be hard for polyrank. And polyrank is actually two tools that are called with iteratively stronger arguments. So there's a little script that calls something called polysys and something called linsys over and over again. And you can see in this case that the free octagon prover is quite bad. Right? So the problem here is that these examples are famously hard. Right? So you have McCarthy 91, for example, and other really tough examples that are that aren't really sorts of things that would show up in programs that programmers write, but are interesting problems. So polyrank smokes everybody else. Terminator does very, very badly in this case. As you can see, it's more accurate. So in some cases, we get proofs from Terminator, but the runtimes are extremely bad. And the reason here is that Terminator is having to do this iterative refinement of the termination argument, and each inclusion check that it has to do turns out to be a call to slam. So we actually have to do predicate abstraction, refinement, and so on during each inclusion check. And if there are many inclusion checks, that means we're doing many, many, many runs of the model checker, which turns out to be slow. Whereas here, even though it's useless, we're getting it for free, right? It's quite fast. Okay, and these are from device drivers. So I took 10 loops out of device drivers and manually removed the pointer aliasing relationships. So tried to just do my best to model the pointer aliasing in some cases. In some cases, I just had to remove them because none, except for Terminator, none of the other tools support pointers at all. So it was maybe somewhat representative of what you would have if you had an abstract interpreter that supported pointers. And so here we can see that the octagon-based approach did fairly well, right? So this, by the way, means counterexample. In this case, the octagon tool doesn't actually produce a counterexample, but it produces two symbolic states and says, I think that your counterexample will visit these two symbolic states. Whereas Terminator actually produces a path through the program. And it's extremely fast, right? I mean, look at the difference here. And it's as accurate as Terminator for these cases. And polyrank is not doing so well. So basically, the story is that we have a technique that's very, very fast, but not particularly accurate. A technique that's quite accurate and produces counterexamples. And we know from previous work that it works for systems code. And then we have a tool that's good for really hard but small termination problems like McCarthy 91 and these sort of classically hard ones. And so now with those three tools together, we sort of have a solution for termination of linear arithmetic programs. Okay, so now we'll move on to the separation domain. So in the separation, so these are there's some tools like Sonar, like Space Invader, and so on that do abstract interpretation where the abstract domain is represented in Reynolds separation logic. And so I have a seed and a well-foundedness check for that domain. So the idea is that the domain is that you have a pure and a spatial part. So here it's just like typically an arithmetic domain. And then here you have formulae that are drawn from separation logic which describe spatial relationships between elements in the heap. So the seed, in this case, is just the pure and the spatial part together with the seeding of variables that are introduced by the abstract domain to represent, in the case of Sonar, to represent the lengths of segments in the heap. So what this particular, the one that this works for, this abstract interpreter does is it introduces new variables, and at the end of the fixed point, it has a set of new variables that don't appear in the program that talk about lengths of list segments or tree segments. And we seed them, we grab them out, and then introduce new variables and set them to be symbolically equal to the values. And then the well-foundedness check, oh, and by the way, this represents the case where the abstract interpreter couldn't prove the program memory safe, so we have to pass that along. And the well-foundedness check just takes the pure part of the formula and it abstracts away the spatial part, and then the pure part will have we'll use the variables that talk about the length of segments in the heap, and then those variables that don't that don't come from the abstract domain will then just be existentially quantified away. So we say that it's a relation from the old depth variables to the current depth variables in pi. And if there are other variables, then the idea is that there doesn't exist. And in the case that the abstract interpreter failed to prove memory safety, then we can't say that the program terminates. We have to say not well-founded. So here we can take a state, some symbolic state. This says that x is a pointer that if you follow it k steps, you'll eventually get to y. So if you dereference it and follow its next field and keep doing that k times, you'll get to y. And in a separate subheap, if you do the same k tick steps, you'll get from y back to x. Right? And this is saying, oh, and by the way, k and k prime are greater than 0. So these are both non-emptyless segments. And so seeding on that just returns the same formula, but now has new variables ks and ks prime and sets them to be equal to the old ones. And then as before, we could symbolically simulate this state across some commands. So we can say what happens when we increment y gets to y arrow next and y is not equal to x. And so that would give us this state. Right? The same as before, except now k is 1 greater than it was before, and k prime is 1 less than it was before. And the reason is that the lengths, when you say y gets y arrow next, the length of this list gets a little bit longer, and the length of this list gets a little bit shorter. Yes?
Why don't you have x excess, and so you have only old k and old k prime? Why not old x and old y?
We could, but in this particular implementation of seed, we've decided not to. So we've decided that that's where you get some level of choice. So you could build a termination prover that also keeps track of something about actually x and y, and so then you need to seed them also. But in this case, we've decided just to keep track of the list segments, the sizes.
Precise answers, or can it also give you answers that are different from this one if you have more variables? Is it monotonic?
It would depend on what your well-foundedness checker says, because your well-foundedness checker has to be hip to the heap, whereas what we're doing literally just pulls out the pure part. So we can call rank finder or polyrank.
Then when you say that you have to invent a seed, essentially you have to come up with a heuristic to select a set of variables from a given set of variables.
Yeah, or you can do something else. It doesn't have to be variable based, right? You just have to produce something in the abstract domain, and then you have to produce a well-foundedness checker that takes something in the abstract domain and returns true or false. And there's some soundness conditions on them. So maybe it's copying of variables, maybe it's doing something else magical, but you have to do.
Do you have an example of something else magical apart from copying?
No, all we've been doing is copying variables, but in theory you could do something else. Right? There's a set of conditions that it has to hold. But I mean, I suspect that typically it'll just be variable copying, or you might do some computation. Right? You might copy some other relationships that hold. Right? Okay, so here's some experimental results with the free termination prover that we get from Sonar. So we took 21 device driver loops and called this termination prover on them. And so the check mark means a proof was found, and the pill means that we found a bug. And this is the number of clouds, right? It's the cardinality of the over approximation. And here's the runtimes in seconds. Okay, and by the way, which one is it? This 20 is a repaired version of 19. Okay, so I'll show you actually 19. So this is a bug. It's in the it's in mouse driver. So I think I have a pointer. So here you can see it's in it's a file called mauclass.c, and this is code that appears. So basically, every mouse driver calls this code. It's some helper code from mouse drivers, and also the same code appears in keyboard class. So every keyboard driver also calls into code that looks pretty much just like this. And the idea, so it's a loop, it's a for loop, but it's operating over the heap. Right? So the idea is that it takes a cyclic list where this is called device extension arrow read queue. So that's this guy. So the variable called entry is initialized to be the forward link. So that's here, forward link of device extension read queue. So we start here, and we're going to walk this list, and we're going to stop once entry is equal to this guy. So and at the end of every loop iteration will increment entry to be the next one. Okay. So to show you the bug, we'll randomly choose one of these nodes. So I'll let entry be this one here. And so imagine now that we're going to execute this remove entry list. Okay, so the idea is that this is a function from the kernel, provided by the kernel, that does pointer swings to remove entries from cyclic lists. So it's a doubly linked list. I'm only showing the forward pointers, but it does the sort of obvious thing where it makes the previous node's pointer point to the forward and vice versa. Okay, so now imagine that we call this IOSIC cancel routine call, and that fails. So we go into this case. Okay, so with this is another kernel-provided function called initialize list head that initializes cyclic. It creates new cyclic lists. So it takes a node and it makes its forward and back pointer point back to itself. Okay, and unfortunately, this aliases entry. So that means that executing initialized list head on entry makes a little self loop. And so what that means is that now this assignment is meaningless, and we're never going to hit this case. Right? So now we're spinning forever. And this is a real disaster because in the kernel, if you get loops that are not terminating, you can't just kill the kernel, or you can't just pull the thread out because it has probably locks open. I mean, it's modifying immutable data structures, and so you can't just if you kill the thread, the operating system is going to go into an inconsistent state, right? So you have to let the thread continue to run, but typically it's gone down and it's taken a resource with it, right? Like the keyboard or the mouse. And so I asked our friends in the kernel team if this was a bug, and they said yes, it is a real bug, and he made an interesting point that it's actually two processors that will be hung, right? So this condition, the reason that call could fail is that there's another thread doing something, and so and it's going to wait forever for our thread to do something, which it's never going to do. So now we're just two of threads are spinning forever, and more importantly. In bugs like this, it doesn't even crash, right? So this is, in some sense, when Windows crashes, it's a good thing, right? Right. You are our model checker, right? So if Windows crashes on you, it tells the kernel team why it crashed, and we've now found a bug, right? Whereas with liveness properties like termination, it typically doesn't crash. It just never moves to the happy state, and the thing spins forever, and in the end people just reset their machine. So we don't get data about when Windows hangs. Right? So these bugs that we've found in the device drivers. These are device drivers that are fairly old and are device drivers that we hand out to everyone else. So they're sample device drivers and also device drivers that run on our machine. And so these termination bugs that we found are actually propagating through the device driver land as people copy and paste the old device drivers into their new device driver, and they modify them and so on. So and we found thus far, I think, 3 or 4 fairly interesting termination bugs in device drivers. A couple with Terminator, and now a couple, and this one we found with a new analysis. Yes?
If Windows would just every few seconds, let's say every 3-4 seconds, record, just take a little interrupt and then record the program counter, then when Windows restarts, it could just see if that was set to something and report that as a location where the machine was turned
So you'd
off.
have some heuristic that said, if we reset the machine and we visited that location, we'll keep a counter on how many times we visited the
Right.
program counter.
And it'll be somewhere around there, maybe.
That's possible. Yeah. I mean, yeah, I can imagine various heuristics. I mean, there's also heuristics that you can do, like with SLAM. You can, for example, try and prove things that aren't quite proving termination, but prove something sort of similar to it. Right? Like if the liveness property is that you want to call after you called some function, you eventually call some other function. You can check some things that will that will be a safety property. The violation will mean that the liveness property didn't hold. So the various approximations of what you could do. But there'll be some noise and so on. Okay, so in summary, I introduced this notion of a variance assertion, which is this binary relation that holds between two pairs of states at a particular location, and showed you how to compute or induce a variance analysis from an invariance analysis. And then showed you how to make termination provers out of the variance analyses. And I think the experimental results show that there seems to be great hope in this line, right, where you take some invariance, maybe an invariance analysis for x86, prove some class of properties at particular line numbers, and now you have a free termination prover for x86, and possibly if some sort of a liveness prover. Now the record winner for termination, right, is one of the free termination provers. It's the octagon. So in many cases, it's the fastest to come up with a proof. And another interesting point is that these new provers, they work in the reverse direction as terminator, and so that's why they're so much faster. So you get the invariance. You get the inclusion for free, right? The inclusion is known by construction, which turns out to be the really expensive part in Terminator, is the checking and the checking and the checking of the inclusion. But it's a little bit less precise because now how the termination prover might fail is it might over-approximate, it might it might add some non-well-founded relations, even though the program itself is well-founded. Yeah, I said that. So Terminator is more expensive, but is a bit more precise. So in some sense, the ideal would be to put them together, to run the imprecise technique, like we do in safety checking. You run some invariance analysis, and then if that doesn't prove the property you're after, then you call some model checker. And so you can imagine the two helping each other out. And in particular, Terminator is more better able to handle these things with complex invariants, such as proving McCarthy 91 or complex pointer aliasing relationships like you see in device drivers. Okay. And I think the last point I'll make is that this is a technique that it's parametric, right? It takes any invariance analysis. It takes any you construct some seed, and typically you can make the well-foundedness checker from any of the known well-foundedness checkers that are available, and it actually just throws away the ranking functions, right? So it doesn't even, like in Terminator, we construct a ranking function and then end up using that in the termination proof, and so then now there's some constraints on how how the ranking function is expressed. For example, is it expressed with multiple 3 or 4 variables per inequality? Or is it linear, for example? Whereas now we're just saying, I over-approximate the transitive closure of your transition relation. I give you a set of things which, if you prove them by any means necessary, prove them all well-founded, then we're done. And I don't even care what the ranking function is. Okay, and the last, I guess one more point, is that another approach which Rushton pointed out when I was working on this 3 or 4 weeks ago is that you could imagine doing a source-to-source transformation on your original program and then just calling an invariance analysis on that program. And that would give you something which approximates what we're computing. But the difficulty with that is that your seed operation then has to statically know what it's going to seed. So for example, with the shape analysis, where during the computation of the fixed point, new variables are introduced, those aren't available to you during this source-to-source transformation, right? So this technique gives us a little bit more power because we can use variables or constructs in the abstract domain that wouldn't exist statically if you just have the program, but you don't have an over-approximation of the reachability. And so that's one point about that. Okay, and then I think that's all I have to say. So thanks very much.